I've got a table of values on the board here, and this is meant to be a table of values for some function of x and y. Okay, so if we said f of xy was equal to z, here's how it works. Okay, these columns correspond to x values, the rows correspond to y values. So then the numbers that I have in here would be the z values. So for example, if I'm in this position right here, I'm in this column, so that x is 1.5. I'm in this row, so y is 2. The z value at that point would be 4. So I would say f of 1.5 comma 2 is equal to 4. Okay, so that's how we're reading this table. Our directions ask us to use the table of values to estimate the partial derivative with respect to y at the point 2, 2. Okay, so if we're doing this, y is going to be our variable, so it's changing, but we're holding x constant at 2. Okay, so that tells me right there, I really care about this column of numbers when x is 2. In fact, I'm going to plot those corresponding points. If I'm in the plane x equals 2, each of these numbers here is going to correspond to a point in that plane. In that plane, that's parallel to the YZ plane, and I'm basically going to have 3 points. I'm going to have a point when my y value is 1.5, when it's 2, and when it's 2.5. So I'm just going to count by a half. So there's 0.5, 1, 1.5, 2, 2.5. Okay, so when y is 1.5 and x is 2, we are at 0. So I've got the point 1.5, 0. When x is 2 and y is 2, we're at 1. So I've got a point 2, 1. And when x is 2 and y is 2.5, we're at 5. Okay, now I really care about what's going on at this point. Because we're in the plane x equals 2, x is 2, and here my y value is 2 as well. Okay, and so I want the point 2, 2. That's the point I care about. What I know is that the cross-sectional curve that I got in this plane would have to pass through these 3 points, and I'm wanting to get the slope of the tangent line at that point. Okay. Now, if I had a formula for the curve, I would, of course, just take a derivative of that formula, and we'd be set. I don't. But I know what the derivative is. It's the slope of the tangent line. Now, to get the slope of the tangent line, I would need to create secant lines using points that get arbitrarily close to this point. I can't really do that, because these are the 2 closest points that I have, but I could use those. So I've got 2 secant lines that I can create here. I could create the secant line between these 2 points, and I could create the secant line between those 2 points. Okay. This would be taking into account the closest point I have that's to the left. This would be taking into account the closest point that I have that's to the right. Both of them would give me an estimate of the slope of the tangent line. If I want the best estimate possible, I would probably want to average those, okay? Because that way I'm taking into account the behavior on both sides of my point. So here again, we're falling back on just some basic principles. The slope of the tangent line is the limit of the slopes of the secant lines. If you don't have enough information to get the limit, you may still be able to get an estimate using just secant lines without taking the limit. So I'm going to say M1 is the slope of this line, and M2 is the slope of that line. M1 would just be rise over run, so that's 1 minus 0 is 1, over 2 minus 1.5 is a half. 1 divided by 1/2 would be 2. So here we get a slope of 2. M2, that's also going to be a rise over a run. 5 minus 1 is 4. 2.5 minus 2 is a half. 4 divided by a half is 8. So I've got one slope of 2, one slope of 8. If I just average them, that's going to be 2 plus 8 divided by 2. That's going to be 10 halves. or 5, that would be the best estimate that I could get for the slope of the tangent line, which is what this partial derivative is. Okay. Turns out, by the way, there is a nifty shortcut for that. If I just calculated the slope of this line, which connects these 2 points, would be 5 minus 0 over 2.5 minus 1.5. It would be 5 over 1. That's going to actually give me the correct thing. So that's a nice shortcut. That's going to work whenever I'm taking 1 point to the left and 1 point to the right, and everything's evenly spaced. Okay, excellent. So you might have a little bit of this, and really the calculations aren't difficult. What's important here is the conceptual understanding of what a partial derivative means, and recognizing that, oh, slope of a tangent, I can approximate with the slope of a secant.